roller coasters, the crown jewels of any amusement park. The steel beasts at Six Flags are notorious for inspiring thrill. Today, we seek to uncover some of the most important physical aspects of modern roller coasters. Our inquiry will focus on two of the park's biggest coasters, Superman and Batman, which we will use to discuss energy and centripetal motion respectively.
Rebranded as Superman in 2016, the coaster has a lift hill of 208 feet, a top altitude of 221 feet, a track length of 5,400 feet, a published top speed of 77 miles per hour, and a duration of 90 breathtaking seconds.
Times mass. Force supply. Oh, let's go, baby. Oh, we're going so high. I have to hold on to my phone. I have to hold on to my phone.
Wow, what a view. This peak of this initial lift hill is the highest point of the ride. The reason that the coaster initially ascends to such a great height is because it must gain gravitational potential energy. At the very top of the coaster, when the car stops right before the 221-foot drop, the car has no kinetic energy and a great deal of potential energy. Is accelerated down the track by gravity and picks up velocity. Its gravitational potential energy is continuously converted into kinetic energy. Now, potential energy can be represented by the formula P equals mgh, where m represents mass, g represents the acceleration due to gravity on Earth, and h represents height. Now, kinetic energy is represented by the formula Ke equals 1/2 m, which represents mass again, v, velocity, squared. Now, because our mass remains constant throughout, we're not losing any people, hopefully, and the car is staying the same mass as we go down the hill. It is our decrease in height and simultaneous increase in velocity that is responsible for the conversion of energy. Now, Six Flags publishes their top speed, which we know occurred at the bottom of the major hill, because it's here that we have no height, and as a result, no potential energy and full kinetic energy, and thus the maximum velocity to be 77 miles per hour. Let me see here. Now, the goal of this exercise is to test Six Flags on their accuracy with our own calculation, with the hope that we will simultaneously be proving the principle of conservation of kinetic energy. According to this principle, when no outside work is done, the sum of our initial kinetic energy and initial potential energy is equivalent to the sum of our final kinetic energy and our final potential energy. Now, because at the top of our peak we have a velocity of 0 and thus a kinetic energy of 0, and at the bottom of our peak, as we mentioned earlier, we have a potential energy of 0 as a result of no height and thus the maximum kinetic energy, we can write our equation according to the principle as 0 plus PEI is equivalent to KEF plus 0. Because again, we have no final potential energy and no initial kinetic energy. Now, substituting in our previous formulas, we can work it out that we have mghi, the initial height, is equivalent to 1/2 mvf squared. Now, because we were testing Six Flags on this number with our calculation, we were trying to solve for vf. Now, both have mass, so thankfully we can cancel mass out. We can multiply by 2, and then take the square root. That's going to give us our final velocity is equivalent to the root of 2 times g times h. Now, the two values we need here are gh. Thankfully, g is a constant on the Earth. It's 9.8 meters per second squared. We calculate this using the universal gravitational formula. Now, our height is published at 221 feet, but we're interested in meters because we like SI units here. So we're going to do some dimensional analysis, knowing that there are 12 inches in a foot and 2.54 centimeters per inch and 100 centimeters per meter, to find that we have 67.4 meters as our height. Now, plugging this in to this formula, which we have derived, we get ourselves 36.3 meters per second as our final velocity. Now, we're trying to compare to Six Flags measured value, so that is no good to us without some more dimensional analysis, to put it into miles per hour. So, we know now that we have 36.3 meters per 1 second. We know there are 1,609.3 meters per mile, and that there are 3,600 seconds per 1 hour. Thus, we can calculate that our final calculated value is going to be 81.2, you can write here, miles per hour. Now, that's a 5.5% error from the published value, which is pretty good. For us, I think that means that the Six Flags published value is pretty good, and our only differences are a result of ignoring things that do work, such as air friction or the fact that we have probably a little bit of height at the bottom here. How energizing. Let's see what this energy conversion looks like.
Built in 2002, the coaster has an elevation of 118 feet, a track length of 2,600 feet, a top speed of 55 miles per hour, and a duration of 140 riveting seconds. The biggest object of interest for us is Batman's large inversion, which is its full 360-degree loop. The car stays in the loop as a result of what is known as centripetal acceleration. The acceleration is dependent on the velocity of the car and the radius of the circle, as expressed by AC equals v squared over r. Centripetal force is any force directed towards the center of a circle. It's basically what keeps us from flying outside the loop and to our immediate deaths, so I'd say it's pretty important. Because Jeff and I are student scientists, naturally we like to quantify items of importance. We need a value for our velocity and a value for the radius. According to the Six Flags customer service team, who we had to call because they wouldn't answer our emails, our radius is about 35 feet, or with a little bit of dimensional analysis as seen here, 10.7 meters. As for our velocity, let's collect some data.
We are using the accelerometer within Kyle's phone with the app Speedbox in order to measure the average velocity of this particular loop. We are also using Wii remote control straps in order to prevent our phones from falling to their deaths.
In conclusion, after recording a velocity of 20.1 meters per second and a radius of 10.7 meters, we can use the equation v squared over r to find our final centripetal acceleration, which comes out to be 37.8 meters per second squared. For bonus points, if the car has a mass of 6,000 kilograms, taking into account the 28 passengers and the cars themselves, according to Newton's second law, we can use the equation Fc equals AC times mass and input 37.8 meters per second squared and 6,000 kilograms as our mass to solve for Fc, or centripetal force, which equals 226,800 newtons.
This project has been a thrill to make,
and we're glad that you could join us for the ride.